Hello students, welcome to the channel Statistica Hub. This is our lecture number 8 in the course SH201A. Okay, so in this particular lecture, we are going to cover something about expectations and variance of a random variable. So let's try to understand like how these concepts are coming up and like what is the requirement of these concepts. That is also an important task. Okay, so let's have a look on this particular thing. If I say like we are given some data set. So let's say the data is something like this. You are given the data set 1, 2, 3, 4, 5. Now you have to find the mean of this particular data set. So how you are going to find the mean? So mean that will be coming out to be like summation of the data over the number of the data. Okay, so that will be coming out to be 1 plus 2 plus 3 plus 4 plus 5 over 5. Okay, fair enough. Okay. Now I will not solving this particular part. I will just going moving ahead and I will introduce like how, like what is the requirement of random variables? Like why do we need the random variable when we are having a lot of things? Okay. So to understand that particular concept, let's try to move on this particular part. Technically, in this particular definition, we are having some given data set and we are given some particular numbers. So you are able to add them. But what if we are having some population data and in the population, we are having the data that is something like this 1, 0, 1, 0, and so on. It is like never ending. Generally, population is something that is infinite, correct? So if we consider our population to be infinite, then this particular formula that we are using, that is no longer valid. Correct? Now, how to use this one? So if I go for this particular form, maybe if I apply the same rule, then the mean of this particular population that will be coming out to be 1 plus 0 plus 1 plus 0 plus so on 1 plus 0 plus so on, never ending over what number we have to divide. Let's say some n. This is going to some infinity. So in this particular context, we are unable to find the mean of the random variable. That makes sense? Okay. So in this particular part, in spite of calculating the mean in this sense, we introduce something like a random variable. So this is also like, why do we need the random variable? So we need the random variable to define or to explain some sort of like population features, because using the random variable is like very important. Like if you are able to understand like how to use the random variable, if you are able to apply like what is random variable and everything like this, then that is like far easy to understand the concepts or the applications of a population. Okay, moving ahead in this part, so we define something that is known as expectation. So we define expectation of a random variable, and this expectation is used to calculate the mean of that random variable. The first thing that you have to memorize, that expectation gives us the mean of that particular random variable. Okay, let's try to have a look on this part. So I know that expectation of any random variable that will give the mean of that particular random variable. So how this is coming up? So you will simply say that expectation of x, that will be summation. We go for x into the respective probability for all the values of x. This is the formula for expectation for discrete random variable. Okay, fair enough. Now moving ahead in this part, so you can simply write maybe x is taking different values. So there will be some x naught into p of x naught plus some x1 into p of x1 and so on. Let's say we are having n possible values. So p of xn. So this is something that I'm getting. Now moving ahead with this part. Now, if I go back to the same problem, we are given some data, and in the data set, you are having observation 1, 2, 3, 4, and 5. And if we try to find the mean, that is coming out to be 1 plus 2 plus 3 plus 4 plus 5 over 5. Okay. Now, if I ask you, I give you this particular data, and what is the probability of getting a 1? So that will be coming out to be like 1 over 5, correct? You are having a bag that is containing 5 different, maybe some sort of cards or something that are having the numbering 1 to 5. And if I say you have to get like 1, what is the possibility? So that will be 1 over 5. We are keeping them like equally likely. Okay, so that is 1 over 5, and that is also equal to probability of 2, that is equal to probability 3, equal to probability 4, equal to probability 5. So can you just write this particular part to be 1 into 1 over 5 plus 2 into 1 over 5 plus 3 into 1 over 5 plus 4 into 1 over 5 plus 5 into 1 over 5. So we can simply say this thing is nothing 1 into its respective probability plus 2 into the respective probability plus 3 into probability plus 4 into probability of 4 plus 5 into probability of 5. Correct. So that's how the expectation is coming up. So we can relate to the same thing that if you go for the population data, then also I'm getting something like this. And if you're given some data set, in the data set, I'm keeping the equilikely concept, then also I'm getting the probability multiplied by the respective value. That is giving me the expected value, the mean of that particular data set. So fair enough, like both the concepts, they're like combined to each other. But in this particular part, you can think one thing, we are keeping the concept of equilikely. But in the context of like random variables, we may have different probabilities. So we are writing in that form. Okay. So using this concept, if I give the population is appearing like this. You are having 1, 0, 1, 0, 1, 0, and so on. So I can see that if I go for 1 plus 0 plus 1 plus so on over some n, that is not giving me any value, no answer. So in spite of solving like this way, we go for like the population. We try to denote this population in the context of some random variable. So you will say that this population, this is formed by a random variable x that can take two possible values, either a 1 or a 0, 1 with a probability p, 0 with a probability 1 minus p. Okay, that makes sense. So in spite of calculating the mean in the usual or the trivial method like summation of the data over the total number of data set, we can simply go for expected value of this random variable, and that will be calculated 1 into p plus 0 into 1 minus p. So I'm getting the value p. So that's how I'm getting the mean. Okay, most important point, like how we are applying the expectation, like what is the need of this expectation. So we go for like the population data. We try to represent the population data in the form of some sort of like random variable. And for the random variables, we are able to define some sort of expectation in this particular manner. And this will be giving us the mean of that particular population, or we can say the mean of that particular random variable. Okay, so I hope this makes like a clear idea, like how the things are coming up. Now moving ahead with this part. So you have to understand few things that if you go for like, okay, for the population, we are having something that is known as population. We are having something that is known as sample. So what's a population? Like very simple problem, or we can say like some introductory kind of thing, like what is a population? What is a sample? So what is a population? If I think about the population, then population is nothing. It is simply the collection of all the objects that are under our study. Okay, but I'm saying it is just the collection of all the objects that are under our study. That is a very important point. What is the meaning of under our study? So assume that like if I go for maybe like currently in India, we are having like the elections going on. So if I go for that particular part, if I had to go for some sort of like idea about which party is going to win, who is going to be the next prime minister or something like that. So for me, my point of interest is I have to check out the population who are appearing for the voting list. Correct? Like we are having the population, we are having the people from the age group maybe 1 to 70. But if I go for 1 to 18, these children or these young kids, they are not eligible to vote. Okay, we are having the voting criteria that a person who is having an age of like 18 plus, he can vote. So in this particular idea, we are having from 1 to 18, this age group people, they are not of my concern. So for my problem or my point of interest, my research problem that I'm going to be making some survey about like which particular party or which particular political party that is winning up, then for me, the population that will be the combination of the people or the collection of the people who are eligible voters. So for me, the population will be coming out for the people who are having the age greater than equal to 18, condition that they are having the voter ID. Okay. Moving ahead with this part, you can have another example. Let's say some particular person who is making some survey on the automobiles. Okay. So for that particular individual, the population will be different kind of automobiles. Okay. Again, like you can have the population to be anything. Just we have to focus on what is our parameter or technically what is our point of interest. So accordingly, we have to define the population and we can give like a lot of things about the population. Okay, so that is something about population. Then we come up close the concept of sample. So what is a sample? So sample is just a subpart of the population. Okay, we are having a like larger group of the population, and practically it is not possible to understand or to analyze the complete population. So we go for like sampling. Okay, we take out a portion of the population, that is your sample, and this sample, this must be a good representation of the population. Good representation of population. Like if I'm having some population, maybe, okay, assume that like being a teacher, assume that I'm having many contacts of the people, and like most of the people, assume that they are like maybe teachers only from my age group, or maybe the older than me, or maybe younger than me, the people like who are in the teaching job. So in this particular part, if I take out maybe the collection, or if you say, sir, just collect some sample from the population of India, like working professionals. So according to like my knowledge, or according to like my connections, if I take out a sample, and in my sample, if assume that we have to take out a sample of 50 people, and I'm taking out a sample of like 40 people who are teachers only. So in that particular sample, this is not a good representation of the Indian population. Like if I go for the Indian population, a lot of professions are there. Like in any population, there will be lot of professions. Some person can be teacher, some person can be professor, some person can be doctor, engineer, anything can be there, right? So if according to like my criteria, or according to like my knowledge or my connections, if I take out the sample that is only taking into account the teachers, that is not a good representation of the population. So whenever you take the sample, it must be a good representation of the population. That is the idea. Now moving ahead with this part, so we are having for the sample, we denote the mean by x bar, and that is simply summation of all the observations over total number of observations. That makes sense. That is very simple, whatever we just covered till now. And for the population, you try to denote, generally sometimes you are given the population to be finite, but if the population is not finite, I am working on the population that is not finite in the context of random variable. So we are going to denote the mean by mean of that random variable mu of x, that is simply expected value of that particular random variable. So that is coming out to be summation for all the values of x in x into probability function of x. For the case of discrete random variable, and we are having the continuous random variable, in that part it will be integration for all the values of x, you do x into f of x dx, that in the course of discrete continuous random variables. Okay, now the point is, always remember this point, the sample mean, the sample mean always exists. You will not find any particular case in which the sample mean is not existing. Like you are having some finite numbers, correct? A sample is something that is finite. A population can be infinite. So if you are having the sample that is coming out to be finite, in that particular context, you are having certain numbers. That can be taking some real numbers. So if you add some finite numbers, again, I'm getting a finite number. So technically, this x1, x2, and so on, maybe xn, these are some finite numbers. So these being the finite, you can simply go for summation of xi, that is coming out to be x1 plus x2 plus so on some xn. And if we add them, that is also coming out to be some finite number. Okay, so if you are given some finite numbers, and if you add them, again a finite number, and if I simply divide that by some n, that is again one finite number, this is again a finite number. So again, there will be the formation of a finite number. So in this context, I can say that the sample mean is something that is always existing. Okay, moving ahead with this part, if you go for the population, so for the population, the mean may or may not exist. So what is the idea of that particular part? So if I go for the discrete case, then we are getting summation for all the values of x. We are having x into probability function of x. So this is some sort of like series. Now, if this series that is coming out to be divergent, so divergent mean to say, if you go for this summation, if this is approaching to infinity, this mean to say the divergent series. So in the course of divergent series, we are not getting a finite mean. So in this particular program, we will be saying that the expectation of x that does not exist. So the expectation exists in that course, we have to write something that this will be the expected value of the random variable x. This is the mean of the population or the mean of the random variable x, and it must be less than infinity. It must be less than infinity. So you can write provided. So if it is coming out to be finite number, then only we are going to say the expectation of the random variable that is existing, and that's how we are going to calculate the expected value of any random variable. Simple format. Okay, I hope that makes sense. Now moving ahead with this particular part. So if I just say one thing, okay. So one example may be if X is a random variable, and if I say it is a positive random variable, okay, then expectation of X less than 0, expectation of X greater than 0. These are two different options. The first option, the second option. So which of these can be like correct? Just think a little bit. Okay, I hope you thought about this one. So technically in this part, the expectation of X that will be greater than 0. How that is coming up? Again, I'm just thinking about the discrete case for the sake of simplicity. So I'm having expectation of X that is simply summation X into probability function of X. So you can simply see the probability function that is always a positive number. And if I say my X that is also a positive number, so this multiplication will always be a positive number for all the values. Now what we are doing, we are summing up for all the values of X. So eventually it will be greater than 0. Okay, fair enough, makes sense, like very simple concept. Okay, moving ahead with the next concept or maybe some sort of transformations. Just assume that you are given some particular constants, maybe some A, B, C. These are some constants. Okay, so expectation of A times of X, that will be simply A times expectation of X. Okay, if you do expectation of X plus B, that will be simply expectation of X plus B. If you do, we are having some another random variable, let's say Y is also some random variable. So expectation of AX plus some BY, that will be simply expectation A times expectation of X plus B times expectation of Y. Moving ahead, if you say you can play with like any of this calculation. So technically, if you multiply, if you divide, if you add, or if you subtract any particular random variable by some other random, by some constant, then the constant will be playing something like this. It will be out of the expectation because the expected value of any constant, that is itself. Okay. Moving ahead, if we are given X and Y, they are some independent random variables, then expected value of X into Y, that will be simply expectation of X into expectation of Y. Okay, we will deal with this part in the upcoming lectures, maybe in the joint distribution part. For now, you can just take this as a like key point or something. Okay, these are some sort of transformations that we make up. Okay, one more important topic that we have to understand is, okay, so if you are given X, that is some random variable, and if you make any function, let's say h of X, that is some function of the random variable X. If this has function, that is some sort of like continuous function. Okay, and I think one also. So in that particular part, if you have to find expected value of this hx, that will be simply coming out to be expected value of technically it will be like, how do we calculate this part? So that will be summation for all the values of X, hx into probability function of X. Okay, so generally, like whatever function they give you, you don't have to check for like, is it continuous or not. So you simply go for this rule that, okay, majorly, like if I assume that the population or the students like who are going through these lectures, they're in undergrad or maybe postgrad, then you may be finding only the simple problems. And on those simple problems, if you are given any function of the random variable, and if you're supposed to find the expected value of that function, so simply do that function multiplied by the respective probability function of X and do summation of X. That's how we calculate the expected value of the function of a random variable. Okay, so that's how these things are coming up. This can be considered to be one function, this can be considered to be the other function. Okay, very simple rule. So this is something about the expectation that we have to understand. Okay, moving ahead, then we are having the concept of variance. Okay, so what is the variance of a random variable? So again, like why do we need the variance or something? When we had the basic idea, like sir, we can calculate 1 over n minus 1 summation xi minus x bar raised to the power 2. So we can go for 1 over n summation xi minus mu raised to the power 2. So technically in these concepts, like we are having the sample, we are having the population that is finite. But what if the population is not finite? In that context, we have to again go for the concept of like expectation and everything. So variance of any random variable x, that is simply expected value of x minus mean of x raised to the power 2. So you can think this is some sort of like function of x. So that will be simply x minus mu of x raised to the power 2 summation for all the values of x, we do probability function of x. Okay, so that's how we calculate the expected value of x minus mu x raised to the power 2. That will give the variance. Moving ahead in this part, so the variance of x that can also be expanded like expected value of x square minus expected value of x raised to the power 2. So that's how we calculate the variance. And the variance of any random variable that will always be greater than equal to 0. And the variance of x that will be 0 in the case of if x is a degenerate random variable. Degenerate random variable. So we are having different type of random variables, different type of distributions that we are going to cover in the next module. But I think I didn't put up anything about the discrete random variable. So I will just give the definition. So a particular kind of random variable with variance of the random variable coming out to be 0, then that is a discrete degenerate random variable. Just remember this property. So you can simply say this x random variable, this is taking a particular value a only with probability 1. Okay, so that is something about the degenerate random variable and the idea of the variance. Moving ahead with some properties of the variance. So we are having certain properties again. Okay, so we are having some x random variable, we are having again some y random variable, some constant a, b, c, d. I don't know how much I'm going to use of them. So if I just say variance of a times of x, that will be simply a square times variance of x. If you go for variance of x plus b, that will be simply variance of x. That means to say if you add something, the variability just remain the same. So idea behind this thing is like, you'll just visualize this part. Let's say x is some random variable that is spread from this point, let's say some point, let's say from k dash to k double dash. This is how the data of x that is spread out. Okay, now if you say that we are going to add b into all the values of x. So this k dash that will be changed to this point, maybe k dash plus b. And this point that will be shifted by b again. So k dash plus b. So earlier the spread was from this point to this point. Now the spread is from this point to this point. So you can see the spread just remain the same. Okay. Now if we combine different random variables, so the variance of a times of x plus, okay, if I just ignore this thing first, if I go for variance of x plus y, so that will be variance of x plus variance of y plus 2 times covariance between x comma y. Okay, moving with this part, if we do variance of x minus y, that will be variance of x plus variance of y minus 2 times covariance between x comma y. Now the point is, if x and y are independent, then the covariance term x comma y, that will be coming out to be 0. And how this is coming out to be 0? Because the covariance of any random variable x comma y, that is expanded like expectation of x comma x dot y minus expectation of x, expectation of y. And in the previous slide, I just wrote something. Where did I write it? I wrote, yeah, I wrote something like this. That in the context of independent random variables, the expected value of x into y, that will be simply expectation of x into expectation of y. So applying this context over there, so I'm getting expectation of x into expectation of y minus expectation of x into expectation of y, we will be getting 0. So in the idea or in the concept, when we are having the random variables to be independent, then the covariance term that will be coming out to be 0. So that's why in these independent random variables, the variance of x plus y, that will be equal to variance of x minus y, and that will be simply variance of x plus variance of y. So that's how we deal with the variance of any particular random variable and the variability concept. Okay, let me cross check. Did I miss out anything that was supposed to be covered in this particular slide? Okay, this was something about expectation and the variance. So again, like the same thing, how do we calculate the variance and everything? So if you go for like expectation of x square, minus expectation of x raised to the power 2. So we already got the expectation of x. Now you simply have to calculate this thing. So that will be simply summation of x square into probability function of x minus mean of x raised to the power 2. But if you are given the continuous case, then everything, the summation, that will be replaced by integration. So in the case of continuous random variables, replace summation by integration. So that's it. The expectation of x square in that part, that will be integration for all the values of x. You do x square into probability function of x dx. Okay, that's about the continuity or the continuous problems. Okay, so these are different random variables, different type of like the rules about their expectation, the variance, the meaning of expectation and the variance. So that's all about this particular lecture, lecture number 8. I hope you're able to understand. Stay tuned. Thank you.